Everyone, we are back and we are at our Pset 3 solution video. So we're looking at determining total uncertainty. We have this expression for bending moment, and let's just kind of flesh it out here. The bending moment is equal to moment BH cubed over 12. Bending moment is equal to MH over 2BH cubed, and then 12, so that's going to leave us with stress and bending, this, so 6, h, and h squared. So basically, it is a function of moment, bending, and h, or not bending, width, and h. So we measured height of the beam 16 times, so I'm going to have some precision in the height, which is going to be our T alpha over 2 nu, S of height over square root of n. There's going to be some precision there. There's going to be precision in the width as well. There's precision in the bending moment. Device used to measure the bending moment, dynamometer with resolution of this. So there is some uncertainty in the moment, which is 15 times 10 to the minus 6 Newton meter. Height and width measured with the ruler with millimeter tick marks. So there's some uncertainty in the h, which is equal to uncertainty in the width, which is equal to 1 times 10 to the minus 3 meters. So we've got the full, we've got everything here. So what we're going to do, and let's go ahead, we're going to actually combine a couple of notebooks because I want to open this lecture 2 as well. So let's go ahead and let's start to kind of set up our solution here in lecture 2 notebook. So what we're going to do is I'm going to switch this over here. So I'm going to say, I'm going to get down to the quantile measurements. All right, so I'm going to say that my sig B is equal to big M, actually I think a capital M is there, M times H divided by 2I, and then we're going to define where I is equal to, so we're going to just do it on the same line. I equals B times H cubed, all that divided by 12. That's I, and then we're also given, let's see, XH is equal to 12 millimeters, so X12 times 10 to the minus 3. We're given NH, height, or the thickness, is 16. SH is equal to 0.2 times 10 to the minus 2. Width is nominally this. Oh, so actually there isn't, so we don't have any precision in the width. So it just gives us the nominal value. So XB is going to be equal to 5.9 times 10 to the minus 2. We're also given NM is equal to 42. We're given XM is equal to 15 times 10 to the minus 3 millinewton centimeter. So millinewton to Newton meter, what is going to be that conversion? Millinewton centimeter. 1 So let's go do that quick calculation. Millinewton centimeter. So we need to do times 10 to the minus 3 times 10 to the minus 2. So let's see. Newton centimeter to Newton meter. So that we know it's going to be times 10 minus 3 and times 10 minus 2, so 10 to the minus 5. So actually we need to do that. So 10 times 10 minus 5. There we go. All right. Let's see, because we know centimeter, 1 divided by 100. Yeah. All right, so we got that, and then we're also given that our S of m is equal to 0.01 millimeter, so it's going to be, again, 0.01 times 10 to the minus 3. There we go. All right, so, and then we're also given device use, so uncertainty in m is equal to 15 times 10 to the minus 6, and then our uncertainty in b is equal to 1 times 10 to the minus 3. Our uncertainty in h is equal to ub. Great. And then we can kind of calculate the rest. So I'm going to start with precision. So there's going to be precision in h, and that's going to be equal to quantile, and then student distribution, student t distribution, and it's going to be, it is going to be my number of h measurements minus 1, and I'm going to do it doesn't say anything, so 95% confidence interval, so 1 minus 0.05 divided by 2. So that's going to be that t value times sh divided by square root of nh, and now I'm going to have to multiply this, or divide this whole thing, remember, divided by my average xh. Great. I'm going to do the same thing now here for precision in m. So I'm just going to change this to nm. Oops. I'm going to change this to sm and nm and xm. And there we go. So those are our precisions. It's in fraction. Now there's going to be our bias, which is going to be equal to square root of, now I have to actually define, so there's going to be bias everywhere. So I'm going to say d sig dm equals derivative of sig b. I'm going to say sig b with respect to m. Then we're going to find the same thing with b and h. b, and then h. Sig b, and then h. There we go. So we'll get all those out of there. So then we'll do d sig b dm times uncertainty in m divided by our equation, which is sig b, because we want it in a fraction, squared. And then we're going to do plus. And then we'll just do the same thing here. So instead of m, h. Ooh, shoot. This needs to be h. So h. This needs to be h. This needs to be h. Oh, that's sig b. That stays. So this needs to be b, and this needs to be b. And there we go. And that should give us our bias error slash dot theta. I'm in my other world right here. B goes to xb, h goes to xh, and then m goes to xn. X capital. Okay, so we can already see that bias error is going to dominate, and so the total uncertainty ub or u-bend is going to be square root of bias squared plus ph squared plus pm squared. And what do you know? How do we want to basically decrease that? Good question. Probably by changing this. So if I were to change this value, it'll probably change this. So fantastic. And that's how you can redesign a experiment using a micrometer. Excellent. So now we're working with a data set, and we're going to perform an ANOVA. So now I'm actually going to go over here, and I'm going to import, I've actually already PS3. We're going to look at this, look at the data set. Let's see how the data looks like. So we have X, Y, Z variable O, and then we have some parameters here. So let's go ahead and let's run through how we can work with that data set. So I want to form, let's do the most general. Now I do need needs ANOVA. I wonder if we have. Let's go ahead. Yeah, let's work with. I want to first, because I do want to make this as straightforward as possible. And let's go ahead and do that right now. So I'm going to go ahead, I'm going to go over here. I'm going to go to ANOVA, and we need needs ANOVA. I'm never sure how to type this. There we go. We got this. So we can look at this data set. So we can select all of this here. So actually, DAT's already pretty much there. So I wonder if we go 2 to -1, we'll probably have everything. Oh, interesting. What's the dimensions of our data? Maybe we need to do, 1 first, and then we just need to flatten it. There we go. So we can run this, and I'm going to actually keep, so I'll keep that code, but I also want to keep, for example, just so that we can remember what's what, 1, 1. Great. So I'm going to grab this code, because this gives me everything. Now what we're going to do is we're going to say, all right, with this data set, and we know that this is X, this is Y, and this is Z, I want all of those interactions, X, Y, and Z, and we've defined those. And we can run, and we can actually see here, all right, statistically very significant, statistically significant, statistically significant, not significant, not significant, not significant, and not significant. If we want the size of the effects, remember we can just do, the size of the effects is fairly straightforward. We're going to take this sum of squares here divided by basically that plus the air. And then we'll get our value, very large effect. We can do the same thing now. The sum of squares for this one, for Y. So X is large, Y is large, and Z, I'm just going to copy and paste over it. Z is also large. So all of these three very large effects. You can kind of see the combinations which can yield essentially the highest outcome. What are we asked to do in this problem? So we did number 1, figured out these, all of them are statistically significant. Size of the effect, determine the set of variables conditions that would produce the highest outcome. So this is where we're going to have to use, actually, our game's howl kind of t-tests. So what we're going to do is we're going to have to do a little bit of work here. So for example, if I look at my DAT1, and I can see, I can pull out basically all the rows in the first column. I have A, B, and C. So what I'll have to do is I need to find, so for example, position of my DAT bracket 1, A. Let's see. And then it'll give me essentially those positions. And then I can extract, and I can do A, B, and C. So I can say X list equals basically list of A, comma, B, comma, C. So that's my X list. And now what I can do is I can say, what about the second? Low, medium, high. So my Y list equals low, medium, and then high. And then my Z list, yes, no. Excellent. So my Z list equals, excuse me, yes, no. Hopefully, let's see if that works. Let's say position, Z list. Okay, so I need a little o. So remember, this is important. Good. So now what I can do is I can say xlist 1. So this gives me all the positions. And I probably just want, I don't think I need the second position. So what I'm going to do is I'm going to say, I want the position here of all, 1. Because I don't really need that second position. I need the second position and the third. So what I'm going to do is this is going to be my positions. So I'm going to say table, and I'm going to repeat this. And there's lots of ways you can kind of do this. So I'm going to say J because I already defined I somewhere. That's actually not good. I'm going to clear I right now. So just to kind of show you what I'm thinking and how I'm going to loop this, let's just go through and do it for one example. So let's just say I'm looking at data set 1, and I'm trying to find those. So I have those positions now. So now what I want to do is I want to extract from dat1 all of these positions. And when I do, I get all of those. So now I know that this is already A. So I'm just going to say, give me all of the rows and the 4th column because I just want the outcome. So now I can look at this. This is like so for example, this is my xlist 1. So that's my first kind of data profile there. So I can now say table and just now repeat this. I don't want to go change this data point here, but I do want to go and cycle through my xlist I. So loop through all the xlist conditions from 1 to length of xlist. And when I do that, and I'm going to do a box whisker chart just to visualize it, but more importantly, I need to actually do this. I need to do a t-test. So I need to say, this is my, for example, x var dat. So for my x var dat, what I need to do is say, I need to do a t-test. T-test. And I need to do, for example, comparison of x var dat 1 to x var dat 2. Are they statistically different? Yes, they are indeed. So now I need to do a table from I and j, and then we need to go from I from 1 to length of x var dat, and then j from 1 to length x var dat. And I want to look at this in a table form. So this is saying all of these are statistically significant from one another, and we can actually do here notched. Actually, chart style. There's a way to do notches. And I know there's a way to do notches because I have it somewhere here. Let me just look at it. Notched. So just need to do, whoops, hopefully I can find this. Let's go. Okay, let's go over here. Come on. All right, here we go. We can look at this. Even though, again, that doesn't kind of take into account. But we see they're all statistically significant from one another. So I want my outcome 3, which is what's my X list? So I need C. So C is going to give me the highest outcome statistically. So I've done that now. So all I have to do now is kind of do the same thing. So instead of now X list, I just need to do my Y list. And actually nothing will change here in this code. So I just changed to Y list. I need to change the length here to Y list. And then, oops, not exactly. And the reason is I'm the position of 2. Because it's the second column now, because that's Y. And now we got it. So looks like high is going to be the 1, but let's go through that. So we're going to say, I'm actually just going to put this in here directly because we know we have it working now. And then we can see the same thing. Numbers have changed, but we see there are still all of those iterations or configurations are statistically significant. So again, I want to do, what is it? I want C high, and then let's see if we have yes or no. Z list, and then I remember I'm changing this to 4, or just a 3, excuse me. Looks like I need no, but let's double check that just to be sure. And then, yep. So C, high, no. Do, re, fa, mi. There we go. All right, so we got it. Okay, variables. Identify the variables and the number of experimental conditions for each variable. So the variables are this, this, and this. Conditions will just be this plus 1, so 2, 3, and 6. Excellent, because those are degrees of freedom. What variable interactions are statistically significant? None. What set of variable conditions will maximize the outcome? Can't really determine that. But if you're just looking for raw numbers, you can kind of look into this table, but we can't do that because we don't know the statistical significance. So that's really not a well-written question. So I wouldn't answer that question. And then 3, size effect of each variable. So remember, we'll take this, basically remember, this of like D type plus this over this plus this, just like you've seen before. So calculate those out and then write out those expressions, and then that's pretty much it. And that's our Pset 3 solutions. So we'll see you next time in Pset 4. Thanks.